let me thank the organizer and Mauro for the kind invitation. And okay, in my presentation, I will change completely in respect to the physics has been discussed so far. I will look at the physical properties in magnetic field, and from the analysis of the physical properties, I try to get information on the system we are studying, that is lantern illuminated strontium titanium interface. And my aim is to answer 3 questions. So the first one concerns the fact that strontium titanate has been discussed as 2-gap superconductor. And can we see signature of that in the magnetic behavior in perpendicular field? The second question concerns the fact of the confinement. So are there effects of the confinement on the magnetic properties? And the third one is, can we learn something about the phase diagram that we produce by field effect in respect to the phase diagram of the bulk strontium titanate. So this work has been done mainly by Alexandre Fett at the University of Geneva, and as I said, it's a transport study of the lantern illuminated strontium titanate interface. As you may know, this system hosts a 2-dimensional electron system that sits in the strontium titanate side of the interface, and at low temperature it undergoes a superconducting transition. Now, what is interesting for us is that this electron gas that self-confine on the osteal side is sandwiched between 2 high dielectric materials, lantern illuminated on one side, and strontium titanate on the other side. So it's quite natural to perform field effects experiment, as you see here in a device, so you can measure transport in plane, and applying just a field across your strontium titanate substrate, you can modulate the carrier density in a relatively large number in respect to the carrier density of the system, and so you can effectively modulate the electronic properties of the system. And if you look at low temperature at the superconducting transition, here you see the effect. So for the depletion state, minus 600 volt applied to the backgate, we see the system is a weak localized conduction regime. As we introduce carriers into the system, as we dope by applying positive gate voltages, we see superconductivity appears, TC increases, reach a maximum, and then decreases as we dope further the system. So we can put TC as a function of the normal state sheet conductance in a phase diagram, and we see that we have this dome-shaped behavior of the superconducting state as a function of the 2D sheet conductance. So on one side we are bounded by the weak localized state, on the other is more metallic state. Now, anyway, this dome-shaped behavior may remind you of the result of 50 years ago by Kunze and Cohen about the SrTiO semiconducting compound that undergoes a superconducting transition at the same temperature, around 300 millikelvin, where here you see TC at the change as a function of 3D carrier density. So again, you have an increase of TC maximum and then a decrease. And so are the 2 domes correlated or are different? So what we can say is that the dimensionality is different. So for the interface, we are in a 2D superconducting system. So here are the measurements of the critical field for the perpendicular configuration. So magnetic field applied perpendicular to interface, where the critical field is around 100 millitesla, and from that we can extract an in-plane coherence length of 60 nanometer, whereas when we apply the magnetic field in the plane of the interface, we see that the critical field reach 1.5 Tesla, and also as a root square behavior in temperature, as is expected for a 2D system. And from this Tinkham formula, we can extract an average or an effective thickness of the superconducting gas that is of 10 nanometer. So with the two-dimensional carrier density and the thickness of the superconducting layer, we can put our virgin samples in the phase diagram of the bulk. And we see that we are here. And now we know that by field effect, we can deplete or accumulate a little bit of carriers around this region in respect to the 3D carrier density, but we don't span all the phase diagram. So why do we have a suppression of TC on both sides? So that's a question I will try to answer with the measurement in field. So what we did was to take another sample, where here you see, okay, the channel, the backgate, and the voltage contacts. We measure the superconducting transition. Here you see as a function of gate voltage, and the color code is, so the blue transition are for the underdope region, the yellow ones are for the optimal dope region, and the red one for the overdope region. So depletion and then accumulation state, the two extremes. Now, if we measure for each one of these doping state the critical fields in perpendicular configuration, this is what we obtain. So critical field versus temperature, you see all, so moving from the depletion state, adding carriers, we see an increase of TC, an increase of HC, and then moving further in doping, we see a decrease of TC. So all these curves are have negative curvature, and this, in fact, is in what has been the analysis on the comparison of what we should expect with a two-gap superconductor. So this has been predicted and studied by Edge and Balasky recently for the SrTiO system and the SrTiO LaAlO interface for a set of different parameters, for the coupling parameters, for the size of the interface, and so on. And one of the signature of the presence of two gap should be this positive curvature of the HC as a function of temperature. But okay, we don't see that for all the doping. We see like this red curve, so more a negative curvature, and this can be due exactly to the fact that we are in a set of parameters that does not allow to distinguish the two gaps. So it does not exclude the presence of two gap, but probably is the set of parameters is hiding the presence of the two gaps. So now, if we extract from the previous curves the in-plane coherence length as a function of the sheet conductance, so we see that the behavior we observe reflects the relation with the gap as we can extract from the TC. So there are no anomalies in the other Doppler regime, so we have both a decrease of the ZC and an increase of Xi, as is expected by the inverse relation. And so we don't see the presence of a pseudo gap, so TC a decrease, but okay, a flattening of Xi, as has been instead proposed by tunnel experiment, where the strength of the gap remain constant in the underdope regime. Now, if we're applying the field parallel to the interface, we confirm that the system remains two-dimensional for all the dopings. So we see this root square behavior moving from the underdope, from the depletion or underdope regime optimally dope regime, and then to the overdope regime. So all these curves have the same temperature dependence. What we see is that they are exceeding the paramagnetic limit, the Pauli paramagnetic limit. So in parallel field, we exceed by a factor of 5 the Pauli paramagnetic limit. Now, this may somehow question the use of the Tinkham formula to extract the in-plane, the thickness of the superconducting gas from the in-plane critical field. Okay, this has been investigated by Harold Wang in a set of samples where we change by growth the thickness of niobium dope strontium titanate film, and he measured the critical field, the in-plane critical field, as a function of the thickness. So he knew by construction the thickness of the film, and he measured the field, and here is reported this relation between the critical field and the inverse of the thickness, and you see that remains the relation remains valid even if the critical field, the parallel critical field, goes beyond the paramagnetic limit. So based on this experimental fact, we analyze our curve in the same way, using this same relation between the critical field and thickness, and so we extract across the phase diagram the thickness, the effective thickness of the superconducting layer. And this is what we observe. So we observe a large region in the optimal underdope and optimal dope regime, where the thickness remain constant between 10 and 15 nanometer. But as we move into the accumulation state, we see that the thickness of the superconducting gas tend to diverge. So actually the gas tend to deconfine into the substrate even more, reaching a thickness of 30 nanometer. So now with this information, we can go back to our phase diagram and compare better the properties of the interface with the one of the bulk. So we had previously just a sketch like that. Now if you look more in detail, okay, the 2D carrier density, that is the red lines, it's continuously increasing as a function of gate voltage, like in a capacitor. So from that value, okay, now we know the thickness for all the gate voltages, so we can calculate the 3D carrier density. And what we see is that, okay, it keeps increasing as the thickness is constant, but when the thickness increases and doubles in the overdope regime, the three-dimensional carrier density actually decreases. And so if we plot now our TC as a function of the 3D carrier density, so the one in yellow, this is what we obtain, TC versus the 3D carrier density. We see is TC is going up, down, and then it's coming back as the 3D carrier density is decreased by the deconfinement of the gas. And what you see is that TC is not even a function of just the 3D carrier density, but there is, okay, some other parameter that we need to take into account to explain why for the same carrier density we obtain two different TCs. And this is what has been done by Davide Valentinis and Christophe Berthaud in our department. So what they've done, it's a model based on the properties of strontium titanate and adapted to the interfaces. So they have taken the electronic structure of strontium titanate with the two bands and two different masses, and they've taken, okay, the relation between in the bulk between TC and the density in order to calculate the pairing potential as a function of doping. And here is where actually the interface sits in respect to the carrier density and so to the pairing potential. So taking this value from the bulk, what they calculated is the superconducting state for a system that is confined in a quantum in a square potential, in a quantum well with a square function. And as soon as you confine into a finite size square potential, what you get is a subband structure of your electronic structure, and these will induce shape resonances. And what they see is that if we take into account the carrier density and the thickness, so they can, the calculation points are the one in green, they can match quite well our experimental points, so the yellow ones. And so taking into account both these parameters, the thickness and the two-dimensional carrier density, we can explain then the behavior of the phase diagram that we observe by field effect. And another point, now if we look this diagram in complete, this is what we observe. So this is all the calculation they did now as a function of thickness, as a function of two-dimensional carrier density, where you see the shape resonance, and you see, okay, the doping effect. that are strongly correlated. And as we move with the field effect, we move along a line along this surface, this complex surface. And so that's the reason why we probably observe this shape. So with decrease of TC in the overdope regime, even if we are far from the decrease of TC in the three-dimensional compound. So the okay, it's an appealing image in the sense that we can now probably try to modulate the system in order to explore more this phase diagram and see if actually it reflects the reality of our system. And okay, with that, I'm coming to my conclusions, and I say that okay, the experiments in parallel in perpendicular field do not show indication of two-gap superconductivity, as has not been observed by the other techniques for SrTiO, both from tunneling or from Squid's experiment. There's been no signature of this two-gap superconductivity in SrTiO or in LaAlO3. Now, also what we don't see is the presence of the pseudo gap in the underdope regime. So we see a relation one-to-one between the in-plane coherence length and the gap in the system. And then, okay, as I said, we have an excess of the parallel field pointing to a spin-orbit coupling into the system. So HC in parallel field exceed the parallel limit, as has been observed also in a thin film of niobium dope SrTiO. And now, taking into account the confinement, the deconfinement effect of the gas across the phase diagram and the carrier density that we modulate with the field effect, we can explain the phase diagram we observe as mainly probably due to a shape resonance of the system. And with that, I thank you for your attention.
Okay, thank you very much for a nice talk.